Okay. The TA is trying to fix the mic. First thing to announce, you can hand in your homework today, or you can do it before tomorrow's exam. No difference. It's just that if you have it, you can give it to me today. For today's lecture, we have 2 hours. There are 2 options that we can do. There are 2 options. One is that we can work on the same problem, but using a different approach. There is actually a different approach for the same problem. I didn't show you last time. So one option is that we can learn the second method, or we can move on to a new topic. So what do you think? Do you want to learn the new method, or a new topic? New method. Raise your hand. New topic. New method. Okay. Some of you want to new method. New topic. Raise your hand. Okay. Pretty even vote. What should I do? How about I cover both? So maybe I quickly go through the new method, and then if we have time, I move on to the new topic. Okay, so for the problem that we did last time, let me brought the file. So the PowerPoint for last time should be this one. Okay. What we did in the same presentation, same slide, what we did was we started from building the shear force diagram. Then we figure out how to take integral to get moment diagram. But today I will teach you a different way. In order to do that, I need to use the board, because I don't think I have a slide for it. So in this second approach, basically, you do not you do not form the shear diagram in advance. You basically directly you try to solve everything directly. The idea is you will try to make several cuts at different positions. And in this problem, obviously, we have point A right here. I should, I think I just draw a straight line. Okay? And obviously, from point B to point C is where you have the distributed load along the Z direction, from D to E is where you have distributed loads along the y direction. Then you have a point F right here. So in this problem, we have different regions. Or different segments. In each segment, we do have different load conditions, different responses about our shear and moment. So I'm gonna call these areas 1, 2, 3, 4, and 5. Okay, so I'm gonna compute the moment responses at different segments. Now, what you can do is to make a cut. So you're gonna make a cut in somewhere at the middle of segment 1. When you do that, you will have, so here is your point A, and here is like where some position where you make the cut. And your coordinate system actually was something like this. This is position 10. And over here is somewhere you can say position X. Okay? And this is your coordinate X, coordinate Y. And what you can do is to start to use balance of moments. You know, should I use balance of, you should use balance of forces, I think. From the previous problem, you already know there is a reaction force going down, and the magnitude is it going down? Yes. 435 Newton, right? So, is it? Let me double check. Yes. So what you can do next is to use balance of moment at any position that you made the cut. So you could be having, let me see, you need to formulate your equation properly. I think I'm not sure which direction is right. So let me just say, I'm assuming there's a shear going up, and I'm assuming there is a moment going this way. So I'm calling this V of X and M of X. So wherever I make the cut, I could be having some shear force and bending moment at the at the edge. I just don't know how much shear and moment I have. I'm gonna use balance of moment to compute everything. But the issue is I'm not sure when I do this whether I'm gonna get the exact same equation. Sometimes I could be getting a completely negative function. That's mainly because when I draw this arrows, I could be drawing an arrow in a opposite direction compared to what I had over here. So I don't want to make a mistake right here. So let me try to compute and see if I matches the equation I have over there. If not, then I need to reverse some of the coordinates. Now, by balance of force, your Vx can only be negative 435, right? That's only, no. You should use balance of moment. So balance of moment. If I have well, let me see. I think you need to do both. If you do use a balance of moment and you have a center point right here at A, then you will be having V of x times this distance. So that would be x minus 10 going counterclockwise in my drawing. And this n is also counterclockwise, so plus mx equals to 0. Okay, so I would need balance of force as well. But if I do that, I can have a different supporting point right here. If I do that, then I have 435 times x minus 10. That is gonna be going counterclockwise over here, and this is also counterclockwise. So if I choose two different positions as my base point, if I call this A point, if this is A point, if I call this a different point, I already have B right here. I'm gonna call this A prime point. So if I choose A as a base, the balance of moment is like this. If I choose A prime as the base, then my balance of moment looks like that. So from here, I do have opposite shear. Why is that? I should draw it, if I draw it in a different way. So it's like I'm studying the element. One is on the right, the other one is on the left. And so it really depends on which one you are talking about. So what I'm computing is the one on the right, but what I'm drawing is the one on the left. That's what's happening. So there is always a reverse. But in this way, I'm not sure if my moment is right. Let me try to compute. So my mx would be negative 3 plus, right? So my mx is right. So the moment I'm drawing right here is right, but the shearing is different. No, yes, my moment is exactly the same as the one I have right here. So that means think this is the end. And this is, shouldn't the shear be up? Let me check my previous slide. I want this to be, I think the left one should be going up. So here should be my shear. So the one on the right should be going down. And this is going clockwise. So whatever I am drawing here should be the external forces. So should I? I think I should draw going this way. V should be this way. In that case, I have a negative sign here. But how come this one goes up? Okay. Yes. It goes up, yes. So this one is going this way, and this one is going this way. Yes. Based on the orientation that we made in the past, if you take a tiny element right here, we would like to name our shear force on the left as positive for going up, and we would like to indicate our moment on the left as positive going clockwise. So on the opposite direction, as a couple, the shearing force goes down and your moment makes a counterclockwise rotation like this, but basically same amount. Since we are, in this drawing, we are observing the external force coming from the right, so we are basically drawing this guy, going down, shearing down, and then bending up from the right. Now, if we do that, the equation is gonna be like these. When I choose A as my base point, V has a counterclockwise moment, so you have a negative sign here to make it, V was having clockwise moment. So if I put a negative sign here, that gives me counterclockwise moment. So the entire counterclockwise moment sum together, you will equals to 0. If you choose A prime as a base, this 435 gives you counterclockwise moment, and also mx has counterclockwise moment. So summing up, that equals to 0. At the end, the second equation gives you mx, and if you use equation 1 and minus equation 2, you will know Vx has to be negative 435, right? If you compare those two. So, at the end, we directly get two equations, and they are matching what we had right here. This guy and this guy. My C2 was here. So you can tell this is a different way to directly compute for shear force and the bending moment. By this way, you don't really need to take integrals. Okay, so you just need to keep on making cuts and then formulate balance of moments, and you should be able to get all the equations. And they are supposed to be the same equations. So let's try to make a cut right here. So another cut. How do you do that when you make a new cut at segment 2? Oh, in fact, since when we are starting region from B to C in the y direction, it has no difference with the first segment because over here there's no forces along the y direction. So if you want to see a difference, you actually would like to see a cut right here. So actually what we had earlier covers the load conditions in region 1, 2, and 3. They all share the same equation. And basically they are the responses along the y direction. Okay? Now, if I make a cut at region 4, so in this region 4, and also along y direction, I should say standing on the xy plane, you can say that. Now I will be making drawings of that cut you made. So this is like the edge, and this is like the cut you made, and this is like point A, and your point D, it could be here. Okay, so somewhere here. And you are making a cut somewhere on the right of D, and here is your coordinate of 10, and this is the other position. I need to compute how much? 10, 90, so 90, 140, 230, up to here is 230. No, 240. This position is 240. Okay? So right here is 240. And the edge has a coordinate of x, some position x. Okay, and here's your y coordinate, and here's your x. Okay, and you know you have a you still have your 435 Newton a single load going down at position A. However, and also similarly, you have a shear force Vx right here. You have a bending moment like this right here. You just don't know what those are yet. From D to some position X, now you are experiencing some part of the distributed load, and they are going up like this. Some portion of the distributed load, and we said they are basically W3 plus W4 in the unit of Newton per, I think, millimeters. So I need to know how large they are. I think is 28. It was 13 and 15. So the total was 28. Okay? If I'm right. Now, what you can do is to do balance of moment as well, but you need to choose some points as your base point. You can again use A as your base point. So if I choose here as my base, then V is making a clockwise moment, so I'm gonna do that. Vx times the distance from here to the base, so it's gonna be x minus 10. This is forming clockwise moment. equals to the ones that is forming counterclockwise moment. Of course, your mx is having counterclockwise moment plus the ones that was contributed by the distributed load. What you can do is to convert that into a single load. So the amount, what you have, the equivalent single load equals to 28 times the width. So what's the width right here? It's gonna be x minus 240. Here's 240, here's x. So x minus 240. So this is how much equivalent single load this portion has. So you convert it into a single load. But the exact position is right at the middle. Right at the middle. So you need to multiply the distance from your base to this arrow in order to realize the entire, how much moment it has. So you are multiplying a distance, that's gonna be 240 plus small, a half of this. So a half of x minus 240, right? You need to do that. No, not, this is not 240, this is 230 here. Because this distance is 230. So 230 plus a half of this small segment, that's x minus 240 over 2. Okay, so that's your first equation. The second one, what you can do is you can choose a base point, maybe choosing here as a base. So here I'm using D as a base. That probably won't give me a easier equation. Maybe I can try choosing the edge as the base. So choosing, I'm calling this point as a D prime, okay? This is a D prime. So D prime as base. Maybe my equations will be shorter. So in total, Vx doesn't form a moment, again, with respect to the D prime base. So only thing that is making, this is counterclockwise, this is going to be clockwise. This will be counterclockwise. So let me do the counterclockwise first. 435 times this entire distance, that would be x minus 10, right? Plus the counterclockwise mx equals to the clockwise. The clockwise will be the one contributed by the distributed load, and we already tried this earlier. So basically 28 times x minus 240, that would be how much equivalent single load you have. Multiplying the small distance right here is gonna be a half of x minus 240. Just a tiny distance right here, right? Solve for those, you will get your M and V. So let's try your mx first. Ms is gonna be whatever you have right here, basically 14 times x minus 240 squared, right? And then minus 435 x minus 10. That's basically it. And if you expand it and collect everything, you have your 14x squared. So you should have 480x times 14. And here you have minus 435x. So do some math. I'm lazy and use calculator. $14 times 480 minus 435. So you have your 6285x. Not the same. Okay. So not the same. Okay, if it's not the same, then I need to figure out why. Let me see. 14 times 480, right? Minus 435. Yeah. Maybe I did something wrong over there? Or did I miss any terms here? 28, this is x minus 240, correct? Correct. And the gap right here, yes, a half of it, yes. This is having x minus 10, that's correct. Round of error? No, I don't think so. Let me need to figure out why. 7,155. The slope was 28, yes. So basically, if this is right, then you plug in, you have your Vx. That's how it's gonna be. But I can observe Vx right here because I have a equation right here. I can compare those two. I can get Vx. But why is it wrong here? Someone is calling me. Okay. Can anyone see why? Especially the second equation. I'm using D prong as the base. That shear doesn't play a role. Only this force going counterclockwise. This is counterclockwise as well. This guy definitely clockwise, so equal sign here. Clockwise, 28 times its width. The width is x minus 240, that's correct. Times the distance, so that should be a half of it. I don't know what was wrong. Negative sign. That's why. That was why. Okay. So 14 times 480 plus 435. 7155. Yes. So negative 7155. Oh. So is it matching? Yes. Good. Okay, just tiny mistake. Now let me finalize it. It's gonna be 240 times 240 times 14 plus 4350. So that will be 810750. C3. Okay, perfect. Very close. Okay? Then I can plug into here. I should be able to get Vx. But if you plug in, you need to resolve some issues that will be very messy. There's one thing that you can do is, let me see how you can make it nicer. No, there's no good way to make it nicer. So, yeah. So I'm gonna write down what you can do for Vx. So when you deal with the first equation, when you try to deal with Mx, don't just plug in the final form. Plug in the ones in the original equation. I think that's easy, that's better. So Mx would be 20a x minus 240 squared. Oh, yeah, exactly this guy. So I'm gonna do I'm gonna do 14 here, and then minus 435 x minus 10. Okay, and over here plus whatever that's here. So you can have 14 x minus 240 squared plus 28 times 230 x minus 240. Okay. Is it easier to solve? No. It's not easy to solve. You even need to do a divided by x minus 10. It's very difficult to solve. Really? Let me double check. If I use this as a base, V goes clockwise. Yes. And then moment counterclockwise, this going counter, so that's why your equal sign is here. Then V is so hard to solve. You need to divide everything by x minus 10. Can this be simpler? The x minus 10 is really making everything so complex. So maybe this is not a good method for this particular problem, because we start everything at position 10. Or maybe we can use a different yeah, that could be better. If I choose the origin as the base point, then I will only have Vx times x instead of Vx times x minus 10. The x minus 10 is giving us a lot of trouble. Maybe. Sometimes the choice of the base matters. Or maybe that's easier for getting the shear force. But you will need every equation on the right to have x. Is it possible?
What is it?
Yeah. Did I make a mistake? Yes.
Did you use the force instead? Balance of force?
I didn't. Should I? Can I just directly use balance of force? Or maybe that's the easier way. If I use balance of force, maybe you're right. So going down and equals to whatever goes up. So 20a times x minus 20. Oh, yeah, is that the answer? Yes, yes, yes. That's exactly a better way. Thank you. So don't do this. Don't do this. No need those. Okay, thank you. You saved my day, right? You saved my video. So it's gonna be like this, and you just need to use your calculator. 28 times 40 plus 435. So 7 minus 7155. Yes. So that's exactly this guy. My C1 was this guy. Yes. Okay. Thank you. Okay, and as you can see, even you use this method, it could be taking a long time. So that's why the last time I would like to show you how to get the shear force first and then take intervals. But when you do use the first method, you need to plug in several points to get a constant. Using what I introduced today, you don't need to take integrals, you don't need to plug in too many points, but you need to formulate balance of forces and balance of moments. And you know that you could be making mistakes like what I did. So you need to figure out a way, okay? I'm not going to spend more time on the third region because it's gonna be very similar. And I don't want to make another mistake again. So any questions? This is basically a different approach for exact same problem using balance of force and balance of moment. You don't need this guy, you don't need this guy, you don't need this guy. Yep. So actually over here you can use balance of force. It's just turned out in the first region, if I use equation 1 minus equation 2, I get V directly. Okay. So maybe please already take a picture? Okay. Because on the video, sometimes the quality on the board could not be good enough. So, should I move on to the next topic? So, the exam stops right here. It doesn't move forward to the next topic. The next topic will be included in the second exam. Okay, but I just want to move on. So for today's lecture, I will be using this particular PowerPoint. Download it. So far we have been talking about I should use a different software to open it. So I can read it like this. Yes. Oh, by the way, can I keep on teaching so we can finish early? Are you guys okay? Yeah. So if you need to take a break, you don't need my permission. So we have been talking about static loading conditions. And we can already break a material by static loads. For example, if I try to break this particular object, if I bend it in a really strong load, I could be breaking this object. Oh, I would like to scroll down this thing, so you don't see what I wrote. Now, when we already know how much stress we could be having inside the material, somewhere, everywhere inside the material, then we can make our design. If the material is not strong enough, we have many choices. We can choose a stronger material, meaning you can change the Young's modulus, choose another type that has a larger Young's modulus, meaning stronger. Or you can change the diameter, change the dimension, make your object thicker, heavier, or you have some other choices. Now, in this particular part of the lecture, we're going to introduce different models. Those models, I call them design models. Those models will help you to make good decisions. So later on, when you decide to make your part stronger, you have some theory behind it, and you know how much stronger you can provide. You don't need to make the material super strong, because whenever you are making a design stronger, it's gonna be more costly. If you make it if you have over design, that means you're wasting material, wasting money. Okay. So for different materials, actually there are different models to be used. So let's take a look at this particular diagram. It came from the book Shigley of the mechanical design book from Shigley's, or entitled with Shigley's. If you have one, you should be able to find this figure. So what's happening is, for some material it's more brittle, some others are more ductile. What's a brittle material? So for example, glasses. If you break the glasses, it basically shatters into small pieces. It doesn't elongate like rubber, okay? So ductile means more like rubber-like. You can lengthen it, but it doesn't necessarily mean it looks like rubber. Metals are, most of the time, they are ductile. You can elongate its length a little bit until it truly breaks. So the way we separate all kinds of materials into two types, one is more like a brittle material, the other one is more like a ductile material, is to study how it fails. So epsilon is the strain. Strain is like the ratio of your deformation. So the definition of epsilon is the deformation over its original length. So F is representing failure. So this means the strain you have when it fails. So if this value is larger than 5%, so for example, rubber probably breaks when it elongates up to 50%. So if you have 1 meter long item, you strengthen, you pull it from left to right, you lengthen it up to 150, and it breaks. Then when it breaks, the strain was 50 deformation over its original length, 50 over 100. So you have 50% of increment of your length. Then your strain was 0.5. Then it was a ductile material. For glasses, it will just break if you have 1 or 2% of deformation, it breaks already. Okay? So that's how you can separate materials into two types. Now, let's talk about the brittle ones, then we can move on to the ductile ones. When we have design models, usually you have two choices. You could be conservative or not conservative. What does it mean, conservative or aggressive? If you want to be conservative, that means you want to have safer designs. Maybe whatever you're designing could cost someone's life, or your design is affecting some, if it breaks, something will be damaged. So you have to be conservative. Your safety factor needs to be high. So for conservative designs, there is a model right here, corresponding model, a proper model for conservative designs. When you, in this table, when you see this no option, that means your design will be less conservative. You could be having more aggressive designs. Usually when you are more aggressive, you are looking for better performance. But when failure comes, you have less safety. So, like riding a bicycle is more dangerous than driving a car. Because when you ride a bicycle, there's no protection, right? So riding a bicycle, you can say it's less conservative than driving a car. Because when you drive a car, you have shields from outside protecting you, the car body. And of course, more materials protecting you, so you spend more money. Okay, so usually, but of course, cars moves faster. So if you, let's say you have a bicycle with a shield, just like a car that has a cover, or exactly same bicycle without a shield. Of course, if you have bicycle crash, you could be damaged more if you don't have the shield. So when you want to have a shield, then the entire bicycle is heavier, more expensive, and you cannot ride it faster because it's heavier. So usually, when you are conservative, you are heavier, safer, more costly, but safer. And on the other hand, you could be having better performance, lighter, quicker, but less protection. Usually that's the case. Okay, now, we would like to focus more on ductile materials. The reason why is, in most of the machines, we are using metals. And metals are mostly ductile materials. So in this book, we mainly focus on ductile materials. And there are two, there's a unique kind of material behavior for different kinds of materials. Sometimes you satisfy this, sometimes you don't. What is this? So S represents the principal stress, Y represents the yielding strength, T represents tensile, C represents compression. So you can either pull your material or compress your material until it's about to yield. And when it's about to yield, the strength, the principal stress that is about to yield is defined as the yielding strength. So there's a kind of material that mostly have similar, very close yielding strength on tensile and compression. When they are very close, it goes to the bottom. There's the other kind, it goes to the top. why do we specifically want to study a kind of material that has similar yield strength on tensile and compression? Because that's easier to analyze. For example, if I have a shaft, I'm bending it. I know on the top, if I bend this way, on the upper edge is having tensile situation, at the bottom is compression. But if I apply the equation, the stress equation for both, from the top, it's gonna be moment times the radius over the area moment of inertia I, so MC over I. That will be the stress on the very top. When I do the same thing for the bottom, same equation, MC over I. However, so in terms of mechanics of materials, the stress equation is the same for tensile on the top and compression from the bottom. However, if a material is having a different strength on tensile and compression, then I need two sets of equations. I need one set of equation for tensile, another set for compression. It's troublesome. So if I'm dealing with a material that has similar yield strength on tensile and compression, then I only need one set of equation. Or if I can assume this is valid, then I can just use one set of equation. My life is easier. So usually on textbook, in lectures, we just assume they are the same. We don't make you guys more difficult to solve a real case problem. However, in the real world, these two numbers could be different. So what do you do when they are different? You either need to check whether your design equation on tensile and compression could be very different. If they are so close, probably it doesn't matter. But if a material that just can elongate better but doesn't compress better, compress less, then you probably need two sets of equations. Or just go to a different model. Just treat it like a ductile material. Oh, no, not that like that. Let's just use a different material. And of course, still a ductile material, but different model. However, in my course, I'm gonna assume these two are so close, so I'm going to introduce one set of equations. And usually there are two considerations. One is more conservative, the other one is not. So first, I'm going to talk about the conservative one, maximum shear stress model. Later on, there's a less conservative one. It's called the maximum distortion energy model. Those are all very popular in mechanical design. Okay? Remember in our pre-test, there is a problem about, do you know von Mises stress? And someone asked me, who is von Mises? What is von Mises? I told him, von Mises is a person's name. So there's a stress named after a person. Von Mises stress is the key analyzing value for distortion energy. So later on, when you learn finite element, most of the time you will study the von Mises stress distribution in a model. That means you are using distortion energy model. Okay, so this model is also very important in nowadays methodologies. Now, let's talk about maximum shear stress model. The concept is actually very simple. Whenever you have stress analysis, you already know how to study its Mohr circle, and you can figure out its maximum shear stress. As long as the maximum shear stress satisfy how strong your material is, you should be fine. But what's the design equation? So our idea came from Mohr circle for tensile test. So remember I told you in the past, if I have a material, I use tensile test to pull it, and when there's no force, my Mohr circle is so small because there's no stress. And when I start to pull it, this Mohr circle starts to expand its diameter. It's expanding its size. However, my second principal stress is always lying on the origin because I only apply stress along one direction. There's no stress along the second direction. That's why my Mohr circle always looks like this. I can continue to pull it, and my stress is gonna be increasing up to a certain point when it's about to yield. So in mechanical design, we don't want to see yielding. You don't want to ride your bicycle until one day, due to a crash or whatever load, if you're too heavy, and some metal part of your bicycle starts to deform and doesn't go back. That's the behavior of yielding. Deformation and doesn't recover back to its own shape, right? So in mechanical design, you never want to see yielding. Of course, you don't want to see breakage. So yielding is already failure for mechanical designs. That's why we don't want to see this Mohr circle to be even larger than the size where this S1 becomes the yielding strength. So the largest tensile circle, the Mohr circle you want to see is when this equals to yield strength. So as the material is about to yield, your first principal stress equals to Sy, basically the yielding strength, and you cannot apply even more stress because it's gonna yield. So you can say that was the state where you can expand your material the most or pull your material the most. You cannot go further. At that particular moment, what's the maximum shear stress? That's basically the radius. At that moment, the radius was half of the S1, or half of the yield strength. So we say this material can only take a maximum shear stress up to half of yield strength. So in the future, no matter how your material is carrying some load, the maximum shear stress it can take, the upper limit, is half of the yield strength. Okay, so we are choosing half of the yield strength as the upper limit for shear forces, shear stresses. That's the first equation, design equation. So later on, if you figure out the stress equals to, for example, MC over I, you can just plug in. So MC over I over 2 must be smaller than your yield strength over 2. Okay, so you could already have some equation like this. MC over I over 2 smaller than yield strength over 2, right? Of course, those 2's cancel out. You have MC over I smaller than your yield strength. So if you already have an equation like this, what does it mean? If you change your material, I should say, let's say when it's about to break, then this is like equal sign. When it's about to yield. right? So if you don't want this workpiece to yield, you want your design to be stronger. So you want to actually see smaller sign here. That means you are still within certain limit, right? So a design equation is usually looking like this, because you can either reach into the limit where it's about to yield, or you're smaller. The load is smaller. Okay? So how can you have a better design? One way is to increase the upper limit. So you can carry more loads, right? So one way is to change your material. You can enlarge the yielding strength by, for example, copper change to steel. Copper is softer, right? Steel is stronger. So the yield strength of copper is lower than the yield strength of steel. So if you have a mechanical design and originally you were using copper, it's too soft, you change it to steel, it's stronger. So that action means you are upgrading the upper limit for that equation. So that's one way to make your design safer. The other way is to have actually so if we use this equation, we cannot easily tell whether I should enlarge the shaft or not, because C is depending on, C basically is your radius. I is also related to your radius. So let's say this is a shaft. We already know this equation equals to 32m over pi d cubed, right? So if you convert this equation into the equation for shaft, then you basically merge the radius or diameter parameter together. So in this particular case, over here, if you enlarge the diameter, the overall left-hand side will be decreased. So when the overall left-hand side is decreased, that means the stress applied to the material will be reduced. And of course, it will be safer. Or what you can do is to carry lower loads. Why would you apply a greater load to the part? Just apply a smaller load. Then you have lower stress. So in our design, there are 3 options already. You can change your material to make the part stronger. You can change the diameter, so make it thicker. Or you can choose to carry a smaller load. Okay? So maximum shear stress model is very simple. Any questions? Okay, good. Now, here comes a weird situation. In fact, when we are dealing with plane stress or plane strain models, I already mentioned we actually have 3 more circles contacting with each other like this. Okay? So sometimes you are just lying on a particular stress plane, and then you are making analysis inside that particular plane. But you probably didn't worry about the other plane, the other 2 planes. And on the other 2 planes, you could be having greater stress. So in maximum shear stress model, there's a concern about stresses in different working planes. So in general, we should be making different assumptions or making various discussions about what are all the possible situations, and try to formulate maximum shear stress equations, and then take a look at all the equations together and figure out how we can have a more general approach, so later on we won't make a mistake by forgetting about the stress in a different direction. So how we are going to do is to have a general Mohr circle like this, okay? So usually, in some of the problems, we are dealing with S1 and S2, and S3 is 0. This is the most usual plane stress problems, okay? So in this particular case, the maximum shear stress equals to the radius right here, so it's gonna be S1 minus S2 divided by 2. So this will be the first design equation that we use. But there are some other situations. Here's another situation. When we have first and second principal stresses positive, and our third principal stress remains 0. In that particular case, the maximum shear doesn't lie on the Mohr circle along the 1 and 2 planes. The maximum shear goes on the other plane. Okay? That's why we need to do this discussion. Because there are situations like this. So in this particular case, still a plane stress problem or plane strain problem, where on the third direction we have no stress. But when you draw more circles like this along each plane, you will realize on the 1-3 plane, we do have a greater Mohr circle and is having greater shear stress. So in this particular general case, the maximum shear is in fact S1 minus S3 divided by 2. Okay. Now things are getting more confusing in the following. I introduced something called SA and SB. Okay. So why do we introduce so-called SA and SB instead of S1 and S2? Because in general, we mostly call S1 as the largest one. But when you change the orientation, your S1 could be, the largest one is always named S1. But when you change how the material is being analyzed, there will be a chance where the S1 change to the other coordinate. So we decided to, for example, put a label on the plane stress coordinate and say, okay, the first one on the plane is A, the other one is B. The A and B label goes with the coordinate. It doesn't swap places. Okay, but when we talk about S1 and S2, the largest one is the first one. So S1 could sometimes be A, S1 could sometimes be B. So that's why it could be a little confusing. But since that could be happening, so we will be making discussions for all situations. So let's say there's a first condition where my SA is the largest one, so SA equals to S1. In the other hand,
SB is S1. So for both cases, you could be having design equations like those two. How come those two? Because in whatever drawing I have right here, my S1, S3 is always 0. So actually S1 should be smaller than Sy. Okay, that's the general equation in this particular Mohr circle. And S1 could be lying on the coordinate of A or coordinate of B. So it's either SA or SB. Okay? So please bear with me and let's see what's happening later on. So let's move on to a different situation where we see one positive S1 and negative S2. In this particular case, my general design equations becomes S1 minus S2 must be smaller than Sy. Okay? And like I said, S1 could be lying on SA or could be lying on SB. That's why these two equations could be swapping SA and SB. I'm sorry, sometimes the A and B are not subscript. It should be, but when I make it, I made some mistake. I didn't correct it. But anyway, you can read it. So then you have these two equations in general for this particular Mohr circle condition. The third one comes with both of your S1 and S2 are negative. In this particular case, the design equations becomes negative S2 must be smaller than Sy. Because your maximum shear stress is right here. The radius could be computed by S3 minus S2 divided by 2. And your S3 is 0. That's why you have negative S2 smaller than or equals to Sy. And similarly, S2 could be lying on A or B. So you again have two more equations. Now we have 4 equations highlighted by those red boxes. I want to put them together. So in general, on plane stress or plane stress problems, basically stress is in a plane. And if I label the coordinate as A and B, these 6 will be the design equations. So what's happening is, I don't even need to care about whether SA is the larger one or SB is the smaller one. I don't even need to figure out. Basically, along the principal stress directions, one of it is the SA, the other one is SB, and then your design equation has to be like this. This is all 6 equations must satisfy. What is the drawing on the right? The drawing on the right is representing the bounded region bounded by the region bounded by these 6 equations on the left. Let's try to study them one by one. If I make a drawing of the 2 principal stresses on the plane, one of it is called SA, the other one is called SB, no matter which one is bigger or smaller. And the 2 equations I had was SA must be smaller than or equals to SY. So that gives me a straight line like this, vertically. And on the right hand side, it's a fail region. On the left hand side, it's a safe region. So we want to have a design on the left of this particular vertical red line. For the second equation, it's a horizontal red line right here. SB must be smaller than SY or equals to. So you can stay on this red line, the horizontal one, or below. You cannot go above. Now, the other two right here, SA minus SB smaller than SY, SB minus SA smaller than SY, that would be the two linear equations right here, these two, and only the area in the middle is safe. Outer area is not good. The other two equations represent two straight lines on the left lower corner. So these six equations forms a closed region right here on the right hand side. Okay? That's the interesting part. In fact, for mechanical design, you can only design inside this region. You cannot make any design outside. If you have any design right on top of the line, that means your design is about to yield. If you have a design inside, then you are safe. If you have a design outside, that means you will definitely yield. Okay? So what would happen if you change your material? If you change your material to a stronger one, that means this red region becomes larger. Okay? What will happen if you try to carry a smaller load? That means whenever you have a design, you may have a point. You may fall on a particular point somewhere inside the region. And if you are carrying a smaller load, that means you are further away from the boundary because you make your load smaller. This point means no load, right? And if you enlarge your load, you could be going any direction. If you go this way, that means your SA and SB are both positive. So you have tensile stress along both directions. If you go this way, that means both directions are compression. If you go this way, that means one of your direction is tensile, the other one is compression. And this similarly. So if you make your load smaller, then your design point goes closer toward the origin. If you enlarge your diameter, similarly the stress goes down, then your design point goes closer to the origin. So when we have design like this, sometimes it's not very convenient because those design equations allows your design to fall on top of the boundary. But on the boundary, you have a really high risk of yield. It's the moment where your material is about to yield. You don't want to be so risky. You don't want to stay at the edge of the cliff. You can just fall. You will die, right? So you don't want to stay too close to the edge. That's why you need to apply safety factor. So what's happening is we would like to give a safety factor on the right hand side at the bottom, and this value must be either 1 or greater than 1. So usually safety factor is a positive value, it's larger than 1. When you have a value that is larger than 1 on the right hand side at the bottom, that means you are enlarging the value on the right hand side. You are pushing your design equation to a higher level. The right hand side, the value on the right hand side is becoming, you are lower because this is a positive value. So you are actually shrinking your design space. You are pulling your ceiling downward. So why do you do that? Because you want your design to be a little bit further away from the edge. Your design region becomes smaller, and you cannot get close to the edge. Okay, so this is the area you want to avoid. You cannot go further here because you will definitely fail. On the dashed line, you are about to yield, but you stay away from yielding. You keep a safety distance. How do you control it? You should make a decision on how much safety you want. So n is representing some kind of level of your safety. When n equals to 1, there's no safety. It's like you can reach to the edge. But if n goes by 2, it's like double the safety. And if you do that, in fact, your design region is shortened, is shrinked, and this position goes half to up to here. So your design space becomes so small. And that's usually the case for most of the mechanical design. We are usually so far away from yielding. Can you imagine one day the elevator, the metal cables yields? Then what will happen? When the elevator goes up to your floor, you see a large gap because the cable elongates. You will definitely not step into the elevator. It's too scary, right? Maybe that was the moment it's about to yield, and you're stepping in, make it break, right? So usually a mechanical design that is related to human life has such a large safety factor. It could be up to 10. That means we are only having our design within such a small area because you divide this value by 10. So your safe region is like so small right here for elevators. Like you're safe, you're so safe. You can never reach to yielding. And that's why a design like that usually can carry you guys for 10 years. Because you're so safe. You're just within this area. But later on, I will tell you in the following subject, 1 or 2 weeks later, I will tell you about dynamic loads. And that's where fatigue kicks in. We need to worry about fatigue. What's happening was whenever a material is carrying some dynamic loads, which means the magnitude of loads changes with time, then the material start to lose its strength little by little. That's the behavior of fatigue. Okay, just like how my lecturing is making you guys tired. Every word I say, I feel a little bit more sleepy. Just how much I can handle is getting lower and lower. How much I can handle this course, my spirit become weaker and weaker. That's fatigue. Anyway, these are the design equations. The final equations for maximum shear stress model. Okay? Now we can come back to the problem that we talked about most recently. This will not be included in the exam, so no worries. But if we want to study this in the exact same problem, earlier we talked about how the Mohr circle could look like in this particular problem. This is the position where we have the maximum stresses, maximum moment. So it should carry the maximum stress. So we draw a Mohr circle at that particular position. By the way, you need to practice it because you need to know how to do this in the exam. You need to know how to draw a Mohr circle. And we computed these, and we know the maximum principal stress was 25. The smallest, the principal stress was negative, almost 0. Maximum shear was 12.6 here, the radius. So how do we apply the design model, maximum shear stress, to the problem? Basically, the idea is easy. I just want to make sure the maximum shear is smaller than half of the yield strength. So if I'm using a material with yield strength of 350, I just divide the value by 2, and I apply a safety factor on the right-hand side, the bottom of the right-hand side. Okay? So in this particular case, you can actually compute N. So in this case, I get a number. N is smaller than 13.89. What does it mean? That means for this particular shaft, if I choose a material of 350 megapascal as the yield strength, I could have, and you apply certain loads like this, static loads, I could have a really high safety as high as 13.89. It's like levels. So what does it mean? That means my shaft is super safe. It's so far away from yielding. And what can you do to save some money? You can change to a softer material. You can even downgrade this the yielding strength to, for example, 200. If you downgrade this to 200, you just have a lower safety, but your material won't fail, because that value will remain higher than 1. As long as your safety factor or the safe level is greater than 1, that means your design is not at the edge of yielding point. Not in the design drawing, you're not at the edge, you're far away from it. So this N is representing like how far away you're from the edge of yielding. So this is just like in this particular design, if this is the edge, you are far away from it. It's like you are dividing this distance by 13, you are somewhere here. You're so close inside. You're far away from it. So what you can do is, if you want to save money, you can change the material you use. You change, originally it was 350, you can downgrade to maybe 200, 200 probably somewhere here. You're still having a gap. You can even downgrade to maybe 100 here. You can still have some safety, okay? So that's the idea. And this is how you can compute the level of safety, okay? Your safety level, safety factor, is smaller than 13.89. What is this? Okay. Oh, that was steel. So I Googled for the yielding strength of steel. That was 350 megapascal. If I change it to PLA, PLA is like the material of 3D printing. PLA was 26.1. Then you greatly reduce your design limit, and now you only have a safety level of 1.04. So if this whole thing is made of 3D printer, then by carrying the same load, it's about to yield. It's about to break, because your safety level downgrades to 1.04. Okay? So what if you are still using 3D printer? What can you do? You use PLA. So what's interesting here is that you can change some of the parameters of your design. You can take a look at the stress diagram here. This is basically the Mohr circle, and this is representing the normal stress that you observe from the right, and the shear stress you observe on the right. So those values could be changed if you change something in your design. And what we would like to introduce right now in this particular diagram is that we want to study the equation over here of your maximum shear stress. This equation will be seen for many times in the future. So I would like you to have a good memory of this. We will see something close to this later on. So if you try to compute the radius of this Mohr circle, actually the equation looks like this. So it's like your design equation is gonna be whatever your normal stress is square over 4 plus whatever shear stress you have on the right hand side square and then square root, smaller than whatever shear stress you have over 2n. So it's more like a general equation in particular shaft problem. Okay, and what you can do next is to plug in your stress and stress equations, the 32m over pi d cubed and 16t over pi d cubed. Plug in into whatever you had in the earlier page. So at the end, you can have an equation of a more complex equation like this. And from earlier analysis, we already know the moment is carrying and the torque is carrying at this particular position. You can plug in the numbers. So over here, you can see all the, and also we chose to stay with 3D printing material, PLA. So my yield strength is 22.1. So only thing left is D. So what you can do is to clean up, just formulate this equation and then try to solve for D. At the end, you realize D must be greater than 49.9. What was the value that we used for the problem? It was 35. It was 35. Okay, so how come the equation goes up to 49? Because in this particular case, we chose to have a greater safety. Over here, we use new numbers, 3. Earlier in the previous analysis, we noticed if we stay with the same dimension, I only have a safe level of 1.04. So I want a greater safety. So my goal is to enlarge the safety factor up to 3, for example. So in this particular case, I'm choosing D as my variable, my parameter to be determined, and I plug in all the exact same values, and I use 3 for my safety factor. In this case, I can use this equation to design for the diameter. I noticed if I want a safety level of 3 under the same load, same material I use, I need a diameter of up to 50. Then I can get a safety level of 3, even if I'm using 3D printing material. Okay, so now you realize how complex everything is connected with each other. Dimensions are here, the moment you are carrying is here, torque is here, yield strength is here, safety factor is here, and they are formulated they're related with each other based on the maximum shear stress model. This is the resultant equation of maximum shear stress model. Okay. Later on, I will talk about different models. The equation looks differently. Okay. So what we'll be learning in the following 2 lectures after the exam, we will learn different equations. And I can tell you, this equation is the most conservative one. We can have less conservative ones. Okay, so that will be covered in future lectures. So as promised, I finished earlier than usual. So that's it for today. If you have any questions about today's lecture, you can come here. I will be staying here for maybe 5 minutes. I think we need to do attendance check, right?
我放桌面，
Okay.
直接丢桌。
So today, not everyone's here. So good for you to collect more points than them. Okay. In my previous experience of teaching the exact same course, usually whoever comes every time pass the course. And usually some of you will give up during the process of taking this course because those mathematics are so annoying and some of you will give up. So usually in this course, I don't even need to make final adjustment of the score. Those who gave up will fail. So I don't need to, decide how to make adjustments. Yeah. So it's good that you are here, and that means you want to learn. Okay, thank you. That's it for today. You can leave after you scan this.